Okay, so this is section 2.5, homogeneous equations and substitutions. This is just the first part of it. We're going to start with homogeneous equations, and we're going to learn solving differential equation by substitution. So we're going to start with the definition of homogeneous. A function is homogeneous of degree alpha if we basically plug in t of x for x and t of y for y, and you simplify it, and it turns out that you can factor out the t to the power of some alpha, and you get the times of function. Then you can say that that function has degree alpha. So let's just look at an example. So here's a function, and we want to know if it's homogeneous, so we're going to be plugging in t of x for x, t of y for y. So instead of x, I'm putting t of x. Instead of y, I'm putting in t of y. And then let's simplify it. So we can see here, this x squared y to the third is our function back. And we have t to the fifth, which looks the same. So it looks like our alpha is 5. So this is basically homogeneous of degree 5. Let's do another one. So here's a function, and let's go ahead and find the function of t of x, t of y, plug it in. And it looks like we've got this back. So yes, it's homogeneous of degree 4. So we plug in, same thing. So we can't exactly factor out a t squared from everything and be left with f of x, y. So this one is not homogeneous. So if you just go back, sometimes you can just look at it and tell if it's homogeneous. So this one was degree 5. You just add the powers. This one is degree 4. This was degree 4. This is degree 4. This one wasn't homogeneous. This was degree 2, this is degree 2, and this is degree 0. So we didn't have the same degree on one of the terms. So it was not homogeneous. Okay, so also first order differential equations that can be written as the derivative, and then we can write it in the form of y over x as a function of y over x, then they're homogeneous DEs. So basically, if it's homogeneous, it could be written in that form. So for the substitutions, I'm going to actually show you two methods. In the first method, we will need the form y prime equals a function of y over x. So after we've verified that the differential equation is homogeneous, like we did above, we're going to use the following substitution. U is going to be this, y over x. That's why we need it in that form. So it's a U substitution. As I said earlier, this is the first U substitution that we're going to learn. When you do a U substitution, you're going to be plugging it into our differential equation. So we're going to be plugging this into our DE, this one. So clearly we'll have to take the derivative in terms of x. Instead of using the quotient rule, we're going to rearrange it, maybe use a product rule instead. So much easier to use the product rule than the quotient rule. U times the derivative of x is just 1 dx dx and plus x times u prime. I just want to mention at this point is we can use differentials, and that's going to be my second method that I'm going to show you. This is going to actually be my preferred method. I think it's easier, but this helps going through it, the first method. And if we're going to use differentials, what this will look like, this would become dy dx is equal to u plus x du dx. And then we can just clear a fraction. So clear out dx, and so we get dy equals u dx plus x du. So this is our alternate method. So going back, using substitution, the dE, which is this one right here, dy dx, remember it can be written in this form. If you write it in this form, this is our first method, is f over y over x. So our dE, dy dx equals, once we put it in this form, when using our substitution, u equals y over x, and using the product rule to find y prime. So y prime is u plus xu, which is dy dx. So that's u plus x u prime. And over here, this y over x is my substitution u. So this is f of u. What we'll want to do is solve this now. Now I'm doing this in general so that you know this can be done every time in general. Let's try to solve this. So I'm going to subtract the u over here. And gosh, it almost looks like it's separable, doesn't it? So let's rewrite u prime. U prime is du is in terms of x, dx times x. Clear your fractions, let's separate them. And it looks like it's separable. Bring the x over here. And the f of u minus u on the other side. So dx over x is du over f of u minus u. So we were able to separate it. Obviously we don't know this function, so we can't finish it off. You just integrate both sides and solve for x and back substitute. But I just wanted to point out these can always be separated because we just did it in general. So if it's homogeneous to the same degree, we will always be able to separate it. So let's go over the process before we do an example, the two different processes. We're going to check for homogeneous of the same degree. We're going to put it in the form. This is what we did above. We're going to use the substitution u equals y over x, but of course we're going to change it to y equals, multiply both sides by x, ux. And then we're going to take the product rule. Y prime equals u plus x u prime, which is just the product rule of that. Or dy dx is equal to u plus x du dx. It's the same thing. And then we're going to separate the variables and solve. Method 2. So we're going to check, same first step. So we're going to use the same substitution, change it to y equals ux, but we're going to use the differential form. So we can take the derivative of both sides, just like you do in Calc 2 when you do a u sub in integrals. Take the derivative of y, it's dy, and we still do the product rule. U dx, derivative of x, plus x, derivative of u, du. Much easier, I think. Again, this is differentials. It's differentials because this is differential form right here. And then our fourth step, same. Separate variables and solve. So it does seem like it's shorter, but what I like about it is this is easier to take the derivative of. We don't forget. And then you're just substituting it in. So let's look at an example. So here's our DE. So our first step is to check homogeneous of same degree. So on the left side, in front of the dy, is 2xy. And if you remember the example above, this is homogeneous of degree 2. You add the exponents. And then the equation on the right, your n. So remember, this is degree 2, this is degree 2. It's homogeneous. They're both degree 2s. So this is homogeneous of degree 2 too. So you could go through and do what I did above, but both of the functions, m and n, have the same degree, so therefore this is a homogeneous differential equation. So I'll do this problem both methods, okay? So let's look at method 1. So just some algebra here that we have to do. I'll admit, sometimes it could be a little tricky getting it into that form. Takes practice. That's another reason why I like the method 2 better. And I think we did it. Now we're going to use our substitution. So product rule. So this becomes, instead of y prime, we substitute it into what it is. And clearly we'll use this. And then we separate. Subtract the u, just like we did up there. I'll just write this as du dx so we can separate them. And then we'll take the reciprocal of that for the other side. So 2u. So we're going to integrate. Looks like we'll have to do a u substitution on the left. But of course we've already used u, so we're on to v. Let it equal to the denominator. So you need your plus constant somewhere. Remember, a to the x plus y is a to the x, a to the y. So this is e natural log of x, e to the c. This c is just some constant because e is a constant. Put that in the front. V, gotta go back substitute, is, remember u is y over x. So we gotta square that. Clear our fraction. And I think we're good there. This is our general solution. So method 2, which like I mentioned, I prefer this one. This is the one I'll start doing from now on. What I just don't like about this method is having to figure out how to get it into this form. Not too hard, and once you've done it, you're good. Just algebra, but we don't have to do that for this form. And this is the way that the book that we're using does it. Is this. We're gonna let, it's the same u sub, same problem, same u sub, which we know it'll work. We've already checked for homogeneous. And then of course this is the same step. Y equals ux. And then we do it using the differential. The derivative of y is dy. Product rule still, u times the derivative of x plus x times the derivative of u. Okay? So this is what we'll use. And this is what we'll use to substitute in to our DE here. So there's no manipulating. We just do it. So anywhere you see a y, we replace it. Anywhere we see a dy, we replace it. Okay? So 2x instead of y is ux. Dy is this. And then 4x instead of y, we do this. X quantity squared, and we keep dx. So now basically all we have here is an equations with x's and u's and du and dx's. So it's just a different variable. And we can now separate and integrate and solve. So let's separate. Maybe not super easy. Doesn't look like it's separable, but it is. So let's distribute. Go ahead and distribute that. Let's bring this, and this on one side. And then we've separated them. And this is the same as above. We can do it real quick. Let v equaling to 4 plus u squared. This becomes dv over v equals dx over x. So v equals ce. Nope, just cx. Remember separating that? V is right here. I guess I can write dv equals 2u du. So u y over x and distributing. Okay, so let's do an example. So first we need to check for homogeneous. And if we want, we can separate this. This is degree 1. This term is degree 1. And the square root of x squared is degree 1. The square root of y squared is degree 1. We have a sum or plus of that. This is degree 1 too. So yes, this is homogeneous of degree 1. We're going to use u equal to y over x. I'm going to use our second method. Convert this to y dy, product rule, u dx plus x du. And then substitute. We're going to basically use this to substitute into our equation. We want to substitute in everywhere we see a y, everywhere we see a y, and a dy. So dy, y, y, factoring out that and pulling that out. Looks like x u dx on both sides cancels if I subtract it. Okay, so now we can integrate both sides. That looks like a trig inverse. Oh yeah, that looks like it's the sine inverse of u. We add our plus c. Back substitute. U is y over x, let's recall. Maybe take the sine of both sides. And we have our general solution at any point of these. But this was an initial value problem. I think it was, let me check this. Y of 2 equals 0. Yes, right there. So if this is 0, this has to be 0 inside here. So c is minus natural log of 2, and we can plug it back in. And if we want, we can actually solve this for y. Can even use the property of natural log. This is natural log of x over 2. And this is our particular solution.